Hi, my name is Teguh. I will be the main course lecturer for this MA 3005 control theory. In this very first session, we will discuss a few things on the introduction of systems, and we will revisit a few parts on Laplace transform. Okay, before we start the introduction part of this course, I would like to share you with an animation to illustrate what controller is. So imagine you are in a room and then you want to have a nice temperature of in your room. So what you normally do, you put an air conditioning system in your room, right? And then if some of you might know, perhaps if some of you have already taken a course in thermodynamics, the main component of an air conditioning system is a heat pump. As implied by its name, heat pump, similar to a water pump, it is transporting a heat from one location to another location. It's like a water pump. It is transporting water from one location to another location. So same to that, heat pump is also transporting heat from your room to outside. And imagine if your air conditioning system is only equipped with heat pump only, with no any other component. What will happen after you run your heat pump? Something undesirable will happen. Your room will be too cold. You will end up into a chilled room, right? Why? Because all of the heat after some time will be taken outside, and then you will end up into this kind of situation. You have a chilled room. You don't like this either. Of course, you want to have a nice temperature. You don't want to have a very cold temperature in your room, of course. So what happened then? In a complete air conditioning system, you will have not only heat pump, but a complete air conditioning system will be equipped with some more components. Okay, the first one is a controller, and then it is also equipped with a control panel, a remote controller, let's say, in your air conditioning system. And if you notice in the indoor component of your air conditioning system, it is always equipped with a temperature sensor. Okay, so how do these components work? Initially, let's consider you have a temperature outside 30 degrees Celsius, let's say 30 centigrades. And then before you turn on your air conditioning system, intuitively the temperature of your room will be more or less the same as the outside temperature. It will also be 30 degrees. This is too warm for you, you don't like it, you want to have a nice temperature but not too cold. So let's say you want to have 20 centigrades inside your room, just a nice temperature for you. So what happened? You will set 20 degrees in the remote controller of your air conditioning system, right? These 20 degrees will be sent to the controller. Okay, and then at the same time, the temperature sensor in your room will sense the temperature of your room, and this reading will also be sent to the controller. Okay, now what happened next? This controller will compare these two temperature readings. 20 degrees, the setting temperature that you set, and 30 degrees, the temperature read by the temperature sensor. The controller will compare these two entities. The controller will subtract 20 degrees from the actual temperature 30 degrees. 20 minus 30, you will get negative 10. And then now, the controller is equipped with some logic. The logic says if the temperature difference between the setting temperature and the actual temperature is negative, so in this case 20 minus 30 is negative 10, the logic of the controller will dictate the heat pump to start. Okay, and then the heat pump will start because the difference is negative. the heat pump will start, and then the heat from your room will be taken outside, right? So now let's say after 5 minutes or 10 minutes, your room is becoming a bit colder because the heat pump is activated. After 10 minutes, let's say the temperature of your room is becoming 25 degrees. The controller will again iteratively read all of the reading. It will compare the setting temperature 20, the one that you set before, to the actual temperature now. The current actual temperature is 25. So 20 minus 25 is -5. Remember, the logic of the controller will say if the difference of these two temperatures is negative, the controller will ask the heat pump to run. So the heat pump is still running. It is still taking the heat from your room outside. So your heat pump is still running, your room is becoming colder, and then let's say after a few minutes more, your room temperature is becoming too cold. It's becoming 18 degrees. It's less than your setting temperature. Okay? The controller keeps read everything. So now 20 minus 18, what will happen? 20 minus 18, you will end up into +2. On the other hand, the controller will also have a logic that say if the temperature difference is positive, the controller will ask the heat pump to stop. And then when the difference is positive, the controller will stop the heat pump. Why? Because the temperature of your room is becoming too cold, colder than the temperature that you expect. The heat pump stops, the heat from outside will flow inside, the room is becoming warmer again. Okay? And then after some time, the room is getting warmer, and then it is becoming 21. 20 minus 21 is -1. The logic of the controller will ask the heat pump to start again, and then your room is becoming colder again. This will happen iteratively, and then expectedly after some time your room temperature will be more or less equal to the setting temperature that you set in your remote controller. Okay, so that is the working principle of the air conditioning system, or in general the working condition of the controller. The objective of this course is more on discussing on how to design the controller. We are not going to discuss on how to design a heat pump. We are not going to discuss on how the thermodynamics of this air conditioning system work, but we will discuss mainly on how to design a controller. Okay? From the illustration that I gave to you, just now, the one that we just discussed together, I can conclude that the objective of this course is more on how to design a controller for any mechanical system that we might dealing with. Looking at the illustration of the air conditioning system that I just shared with you, I can deduce a definition of this control theory, as you can see in these slides. So by definition, a controller is a device. It can be in a form of a small computer, microprocessor, or just a simply normal computer, which monitors, in our previous example, we monitor the temperature of the room, and physically alters our controller together with the heat pumps will alter the operating condition of the heat pump of the given dynamical system. So a controller, again, a controller is a device which monitors and physically alters the operating condition of a dynamical system. Looking at this definition, you can see two main keywords. The first one is a controller. The second one is a system. Why do I in particular highlight these two keywords? It's because a controller is designed only for one particular system. most of the controller is not interchangeable. So if you are designing a controller, you will design a controller for one particular system. That means when you are designing a controller, you need to understand the behavior, the properties of the system in which you are designing the controller for. For that reason, this course will focus on two things. The first one is system. The second one will be on designing a controller. In these sessions and the next following session, we will discuss mainly on the systems first. Okay, and these will be the textbooks or the references that we use. We will mainly use the textbook from Kazuhiko Ogata. It's a modern control engineering. It's a nice book. You can easily read it. But in addition to that, there are some other relevant references that you can use. Among many references, the one that I also normally refer to is the one from NIST, Control System Engineering. These two books, the first one from Ogata and from NIST, discuss not only system but also how to design controllers. In addition to that, there are also some other references that you can use. System Dynamics, also from Ogata, this discuss mainly about dynamic systems. And then from Charles, Modeling and Analysis of Dynamic System, this might give you also some more ideas about the dynamic system. But of course, beside all of these references, you are free to use any text, any reference on dynamic system and on control. Okay, so as I have already mentioned before, these particular sessions will discuss mainly on systems. So then at the end of this course, you should be able to first differentiate static and dynamic systems. There are two different types of systems. We will discuss this shortly. And at the end of this course, you should be able to identify the relevant mathematical background to describe a system for both static and dynamics, of course. And then it is expected that at the end of this course, you will also be able to develop a dynamic system, the dynamic model to describe dynamical systems. Okay. And then the last point, as an outcome of this course, you should be able to analyze a response of dynamical systems. Okay, as a prerequisite of this course, you need to have some knowledge on mathematics, of course. Please pay more attention on three things that you have already learned from mathematics. Calculus, we will deal a lot with differentiation, integration, so you need to have a strong fundamental on calculus. We will deal a lot also with complex number operations. And then the last one is on Laplace transform, one of the tools in analyzing a differential equation. Okay, and this will be the entire lecture map. We will start with introduction soon, and then we will discuss Laplace theorem, and then we will discuss one by one all of different types of system until the end. So I will split this course into 8 different topics.